Hi everyone. Today we're presenting our research on optimizing residential insulation to reduce both energy use and housing costs, with a focus on affordability in Charlottesville. Across the U.S., housing is becoming increasingly unaffordable. According to the U.S. Census Bureau, nearly half of renter households spend more than 30% of their income on housing. At the same time, housing prices have increased dramatically since 2020, while median incomes have remained relatively stagnant. But here's the key issue. Low upfront construction costs often lead to higher long-term operational costs, especially during energy bills. Especially energy bills. Low-income households experience an average energy burden of around 11%, which is 3 times higher than non-low-income households. That means inefficient housing disproportionality affects those who can least afford it. This becomes especially critical in Charlottesville. Low data shows persistent cost Local data shows persistent cost burdens rates near 50% and rising homelessness following the closure of low barrier shelters. Construction costs continue to delay permanent supportive housing projects. So we're facing two extremes. Traditional homes, lower upfront costs, high long-term energy use, or passive homes, lower operational costs but high initial material costs. Our research asks, is there a middle ground? Can we optimize insulation design to reduce energy consumptions without requiring expensive high-tech passive materials?
All right, so for part two of our project, it's going to be called the method. To answer that question, we developed a multi-objective optimization model using parametric modeling tools in Grasshopper, along with Ladybug and Honeybee. Our model focuses on the thermal envelope, specifically the insulation layer of an exterior wall. We vary these three primary insulation properties: thickness, conductivity, and density. We then evaluated three objectives simultaneously. The first one is energy use intensity, or EUI, thermal comfort measured using Fanger's PMV equation, and material and operational costs. Thermal comfort was constrained to follow ASHRAE standards, keeping PMV between negative 0.5 and positive 0.5. We also aligned heating and cooling thresholds with standards from Passive House Institute US, or PHI-US, which sets annual energy demand and airtightness guidelines for high-performance buildings. Using Latin hypercube sampling, we tested 2,000 combinations of insulation parameters and generated a 3D Pareto front. This allowed us to visualize trade-offs between cost, energy, and comfort. Instead of forcing one perfect solution, the model identifies optimal trade-offs depending on the weight given to each objective. This makes the tool adaptable whether the priority is minimizing costs, maximizing comfort, or reducing energy.
To validate the model, we compared our EUI outputs against the published case study conducted in Seoul, Korea, using the same wall U value of 0.25 watts per meter squared Kelvin. We tested multiple combinations of thicknesses and conductivity that satisfied the equation U equals K over D. Our model produced EUI values within approximately 1 to 2% error of the published study, confirming strong predictive accuracy. Sensitivity analysis did show that our model responds more strongly to insulation thicknesses and conductivity than the reference study, which suggests that incorporating additional real-world variables could further refine accuracy. Even so, the key finding is this. By optimizing insulation thickness and material selection without relying exclusively on expensive superinsulated passive systems, we can significantly reduce energy consumption and operational cost while maintaining thermal comfort. Looking ahead, we will be extending this work within the A School by modeling hemp-based insulation systems as part of a parametric framework. Hemp insulation is particularly compelling because it offers low embodied carbon, biogenic carbon storage potential, vapor permeability beneficial for wall assemblies, and competitive thermal conductivity values. By integrating hemp insulation into the same optimization workflow, we'll be able to compare its performance, cost efficiency, and comfort outcomes directly against conventional materials. This allows us to evaluate not just operational energy, but also broader environmental impact, bridging affordability, performance, and sustainability. Ultimately, our research demonstrates that insulation design is not just a material decision, it's a financial, environment, and social equity decision. And by embedding optimization tools into accessible design workflows, which is what this research and this tour is all about, we can help make high performance housing more affordable and more widely achievable. Thank you.